Hi, this is a video for COMP345. This is for week 7, slide 7. There's going to be 3 videos for this slide set. This is video number 1. So in here, we're going to talk about in C++, how C++ does polymorphism by using virtual methods. And we'll also talk about a related concept of abstract classes and how you do that in C++ and what that means. Eventually, one of the things we're going to discuss in the further videos is how the mechanism for the implementation of polymorphism is implemented in C++. As for many things in C++, it's important to understand how it works in order to use it properly, or at least figure out why things are not working properly when they don't. Okay, so let's go to the slides. So this is a slide set is talking about polymorphism and virtual functions. Eventually, we're going to talk about the related concepts of abstract classes, value and reference semantics, the related concept of object slicing. Then eventually, we're going to talk about virtual function tables, which is the way that vast majority of compilers are implementing the dynamic dispatching. This relates to or uses function pointers. So I'm going to provide you with a slight introduction to what is function pointers in C++ before we talk about virtual function tables. This video is only about these 3 topics here of this slide set. So what is polymorphism? So polymorphism is essentially, as the word says it's something that has many shapes. In terms of programming languages, what that means is that you associate different meanings with one function, and this is always across an inheritance graph. Okay, so inside of a graph, you have one function that has the same name that is shared between the parents and the children in the graph, and then using some kind of mechanism, you are able to figure out which one you mean in the specific context in which you are calling it. Okay. So this is, as I'm sure you already know, this is a fundamental principle of object-oriented programming. Doesn't mean that some programming languages don't have polymorphism. That doesn't mean they're not object-oriented. Object-oriented programming does not require polymorphism. Of course, it's a thing that you can enable, requires quite a bit of work in terms of implementation, but it's not necessary. But most object-oriented programming languages would provide it, including C++. One of the things that complexifies things, as always in C++, in polymorphism, is when you have multiple inheritance. Thing is, as you have different functions with the same name, so depending on what context you are calling them, you might bind to one specific version of these functions. So this, in most cases, cannot be determined at compile time. So that's why it requires some mechanism to be in place at runtime to do this binding. So that's why we're talking about runtime binding mechanism here. So when you don't have polymorphism, the binding can almost always be done at compile time. However, due to the nature of polymorphism, it requires a runtime binding mechanism, which might be costly to implement, to run. Okay? For example, as we will see, when you have runtime binding in C++, that requires additional information to be stored in every of your objects that can be the subject of polymorphic calls. So yes, there's a cost involved in polymorphism. Okay. As we will see later, you can actually in C++, which is quite exceptional and across all object-oriented programming languages, in C++ you can have this dynamic binding that is enabled or not enabled, depending on how your code is designed, as we will see later. So this is a good particularity, something that sets C++ aside from many of the, or most of the other object-oriented programming languages. So yes, polymorphism needs to be somehow enabled in order to be available at runtime. Again, this is due to the fact that when people designed C++, there was efficiency in mind. As I just mentioned, when you want to have polymorphism, that requires more data to be stored in your objects, as well as the execution of this dynamic binding mechanism at runtime, which makes the program somehow consume a little bit more memory and run a little bit slower. So if you don't use polymorphism in your program, the objects don't store this additional data, and there's no runtime binding that is happening. Okay, so being able to turn it being able to turn it on or off, it has a definite efficiency advantage. So in C++, the dynamic binding, this branching, runtime branching mechanism is called dynamic binding or late binding. There's lots of different words to refer to that kind of mechanism. These are particular terms that are used by the C++ community. This fact I was mentioning about earlier, about the fact that you can turn on or off the polymorphism, has to do with what is called value and reference semantics. So you can use either value semantics or reference semantics, as we shall see in the second video. Or reference semantics is when you use pointers or references to declare and manipulate your objects, whereas value semantics is when you don't use pointers or references. This has a very dramatic difference. It's very important to understand the difference between the two. If you use value semantics, there's actually no polymorphism that's happening with your objects. So you have to use reference semantics if you want to have polymorphism. So this is implemented in C++ as with many other programming languages, using the notion of virtual functions. Okay, so you declare some of your methods as virtual. Okay, here I say virtual functions, but actually there's no such thing as a virtual free function. Polymorphisms only applies when you have inheritance. Okay, doesn't make any sense to have polymorphism without inheritance. Well, depending on how you define polymorphism, but the classic polymorphism is using inheritance. That's why polymorphism applies only to virtual functions, which are methods. So what does this keyword virtual mean? So virtual, if you look in a dictionary, actually means that something exists in essence, but not in fact. So you have some kind of concept of a certain method, but you don't have an implementation for it. Okay, so that's what is virtual actually meaning. Or you may have an implementation that exists, but then it would only be, when you will call it eventually, it's going to be the most specific version that is going to be called, as we will see later. Okay, and then you also when you want to use polymorphism in C++, you have to declare some of your methods as virtual. If none of your methods anywhere in your hierarchy has been declared as virtual, there's no polymorphism that is involved, and there's not going to be dynamic binding during runtime. Okay, so if you want to run a leaner code and you can do away with polymorphism, avoiding polymorphism is a way to have code that runs somehow faster and consumes less memory. So if efficiency and memory consumption is a great concern of yours in your design, you should not use virtual functions. And then you can also have what is called pure virtual functions, which is a way that in C++ you actually create abstract classes, as we will see later. So what is polymorphism? Let's use an example to explain that. So the typical example is the shapes example. That's what's behind me here. So you have the notion of a shape. And by shape, we mean geometrical shapes. So you can have a circle or a rectangle that are both different specific kinds of shape. Okay. The idea in this example is, of course, that, for example, when you have a circle or a rectangle, there is the get area member function. And of course, as we all know, there's a different formula that you should use to compute the area of a circle versus the area of a rectangle. There might be also some data members which are different. For example, a circle has a radius whereas radius doesn't make sense for a rectangle. Okay. So there are differences and commonality between all these subclasses. Okay. The particularity of the example we're going to concentrate on is the get area and the print function, which will eventually show that should be implemented using polymorphism. Okay. So eventually what we figure out is that if you want to make this work, then you should have one get area for circle and one get area for rectangle. So I might as well, not implement any get area for shape and then provide get area for circle and rectangle. Okay, so that would allow me to declare a rectangle and a circle and then call get area. Okay, note that here this is not polymorphism. Why? Because get area are not connected to one another. Okay, it starts to go towards polymorphism if you would have a get area that is here, okay, as we shall see. So at this point in time, when you have this here, get area, the two get area functions are not related in any way. Okay, so that's not polymorphism. And here, well, how do you determine which get area is going to be called? Of course, here you determine it by the type of the variable that you're calling it or the object that you are calling it from. So R is of type C rectangle. So we're talking about here C rectangle : get area. Whereas here we're talking about circle : get area. Okay. So it has to do with the type of what's on the left-hand side of the dot operator. Now, there's a problem if you want to proceed this way. One of the main problems is eventually what's going to happen when you want to add other subclasses. Okay. Another problem is when you want to print the object or the characteristics of the object, as we will see on the next slide or the further slides. Eventually what's going to happen is that the print is going to, for example, want to print out the value of the area of the circle or the rectangle. Now, as we saw, so here we're talking about a print function at the level of the shape. Okay, so shape has its own print function, and then depending on if the object is a circle or a rectangle, it's going to print the area using the formula that is specific to circle or rectangle. And also when you want to print, if you want to print, for example, the width and height of the rectangle, then in the print here, you're going to print width and height of the rectangle here, whereas here you're going to print the radius of the circle. Okay, so there's different things that you want to, different values that you want to print, or different functions that you want to call that are specific to each of the different subclasses of objects. Okay. So here you have a function that exposes common behavior in a base class that uses another function that exposes subclass specific behavior. So this print function here, when it calls get area, it's going to want to call the get area of a circle or get area of a rectangle. So even though this is common behavior, it wants to use the specific type behavior depending on which kind of shape that we're talking about here. Okay. So we may say, okay, we're going to use our dynamic cast here. So when you call print of a shape object, then it is going to create two pointers to this shape object, and then it's going to check if these two pointers, for example, if it is a circle, then you're going to print these things here. For example, the get area and the radius of the circle. And then if the object is a rectangle, then you're going to print the width and the height and the area of the rectangle. So you see here that you're calling get area, get area. So which get area that you're talking about, here you basically use the dynamic cast to translate or to transform the type of the object from C shape into a circle. If that's successful, then this P1 is going to be non-null. So then you're going to execute that here. If the object was a rectangle, then P2 is going to be non-null, and then P1 is going to be null. Okay, because remind you that dynamic cast, when you want to use dynamic cast on a casting that is invalid, it actually returns null. So if you're trying to print a circle and then you're trying to transform it into a rectangle, this is not allowed because there's no inheritance relationship between circle and rectangle because they are siblings. Okay. So yes, this code actually works. But the problem is that, as we shall see later, is that if you want to add a new class later on, if you want to add a triangle, then you would actually, by adding triangle here, you would have to change the code of your function print and add another block here for if add a triangle here and then have another if here for dealing with triangles, okay, which is not very good for the modularity and the maintainability of your code. Because here, all you want to do is add a new class here. It forces you to change the code of the superclass. You try to avoid that. Of course, as we will see later, polymorphism would be the solution. So, there's nothing wrong with this code in the sense that it doesn't work. It actually works, but it's not very maintainable code. So yeah, so if you want to add a new class called triangle, then function print here. So the function print for the triangle, it needs to actually, when you run the code for the print for shape, it will need to be changed so that it actually also works for triangle. Okay. So eventually what you want to do is to have some kind of mechanism in place at runtime so that it will automatically branch to subtype specific behavior, which is somehow the definition of what is polymorphism. When you have ambiguity between functions of the same name across a hierarchy, if those have been declared as virtual, as we saw, then there would be a mechanism that will make the right choice, which is your dynamic binding mechanism, which is implementing or making polymorphism possible. So if you want to add triangles inside of your hierarchy here, then you would have to add in your print function at the level of the shape, you would have to add this line here and then add this block of code here. Okay. Anytime you want to add a new subclass here, then you would have to make the change in the code here, which is not very well maintainable. So that's not the solution. It works, but that's not a very elegant solution. So the solution is to use what is called virtual methods. You certainly have seen for Java, there's also virtual methods. That's exactly the same concept, but as we will see later, it's not implemented in the same manner. So virtual methods allow to declare functions whose runtime behavior uses a subtype specific behavior. Okay, so if you want to enable polymorphism in C++, you need to have somewhere in your class graph, you need to have some virtual methods. If there's 0 virtual methods, there's no polymorphism. So the idea is that you will eventually create a variable that is of the supertype or the base class, and then you're going to instantiate this superclass type variable with an object of one of the subtypes. Then when you're going to call the functions inside this object, then the dynamic binding mechanism is going to basically branch or bind the function that is subtype specific, even though the variable that you declared was of the base type. Okay, so that's basically what is polymorphism achieving. So the mechanism, I repeat, for C++, the specific name in C++ for this mechanism is called dynamic binding or late binding. What's the meaning of dynamic binding? Anytime you talk about dynamic in terms of programming language terminology, generally that means something that happens at runtime. Whereas if you would have static binding, that would be binding that happens at compile time. Static is compile time, dynamic is runtime in general. Okay, so that's why dynamic binding is binding that happens at runtime. Now, what is binding? Binding is essentially when you're calling a function, like for example, if you define a function body across different compilation units, then the compiler will compile each of the different compilation units. And then there's going to be some functions inevitably that are called from this compilation unit to this other compilation unit. Now, binding is the act of actually binding this function call in the compilation unit here to a function that is defined in another compilation unit. So this action of connecting these two is called binding. So dynamic binding is this action, but that happens at runtime. In many cases, you can have static binding at compile time or by the linker, but if in cases where that's not possible, such as for polymorphism, then the binding happens or has to happen at a runtime. Of course, this binding is, it's a procedure that you run to actually figure out which function should be bound to a certain function call. So in order to make this computation, you require some data and you require to execute some kind of procedure. Okay, so that takes time. So that takes time. It requires a little bit more memory to make the decision happen. That's why enabling polymorphism is a little bit less efficient than if you don't have it. That's why the C++ designers have made the decision to only enable the dynamic binding mechanism at runtime only if polymorphism is present in the code that you've compiled. If there's no virtual functions anywhere in your code, then dynamic binding is basically not part of your runtime system. It's never going to be used. There's not going to be memory that is consumed in order to deal with it. It's going to be basically running without any of the resources necessary to have dynamic binding happen. That's a very good example of how C++ was designed in a very lean manner. It's a very well optimized language, or a language whose execution is very well optimized. Okay, so in C++, this is a very important something that often people don't really understand. How do you enable polymorphic behavior inside of a C++ program? For example, if you're declaring a Java program, this dynamic binding or dynamic binding version of how Java does the polymorphism, it's always Java by default always uses dynamic binding. Okay. So there's no turning it off in Java. It's always there. It's always how all the functions are being bound or branched upon. So in C++, there has to be some conditions in place for the dynamic binding to be turned on somehow at execution time. So first thing that must be there is that you are using pointers. Okay, if you're not using pointers or references in C++, dynamic binding cannot happen without pointers or references. Okay, so if your code is devoid of pointers, there cannot be any polymorphism in your code. So first, you declare a pointer to an object of the base class type. So you declare here an object, or here it's an array of pointers to shape. Okay, so these are pointers, an array of pointers to objects of type shape. Okay, and then eventually what you will do is that inside of this array of shapes, you will put a rectangle, a circle, and a triangle. Okay, so here what's happening is that you have a pointer to a shape, which is the superclass, which you instantiate with an object that is of one of the subtypes. Okay, so that's always what you should have when you want to have polymorphism in place. Okay, your variable that you declare in which the polymorphism is going to happen is going to be one of the base classes, whereas the object that you put into this variable is going to be an object of the type of one of the subclasses of this base class. And it's always going to be a pointer to the base class object. So that's basically the two components, the two conditions that you must have in place for the polymorphism to be enabled. Plus, as we will see later, you need to have virtual functions. So this is also applicable to when you pass an object by reference or by pointer. Okay. So for example, if you declare a function that receives, let's say, a pointer or a reference to the base class, and then you, for example, you have a function that receives a pointer to a shape, and then you pass it a rectangle object, then polymorphism will be enabled somehow inside of this function. Okay. Why does it have to happen dynamically at runtime? Because once you declare this object, for example, this array of pointers to shapes, at this point in time, you have no way of determining what kind of objects you will actually put inside of this array of pointers to shapes. Okay, so you can put any of the subclasses objects in. You can make these pointers point to any of the subclasses of shape at any point in time at the execution of this program. Okay, so there's no way you can predict which one is going to be which. Okay, so that's why the decision has to be done at runtime. When the object is actually in there, then you can make a decision according to what the object is pointed to by these pointers at runtime. So you cannot predict that at compile time, so that's why the decision has to be delayed at runtime. Okay, so if you have, and you should have some virtual methods, if a method has been declared virtual, generally in the superclass shape here. And if you call this method, then the subclass behavior, the specific subclass behavior is going to be called. So even though you call, for example, you may have declared your object of type C shape. So the type of each of these pointers here is a type is pointer to C shape. Okay. So when you actually call get area here, it might appear that it's going to be the get area of the shape that is going to be called, but no, because shape as because get area, as we will see later, has been declared as virtual in the shape class, then it's the subtype specific behavior that is going to be called. So in this case, for example, for the first pointer here, it's a rectangle. So when you call get area here, it's going to be get area of a rectangle that's going to be called. Here, the second one is a circle. So when you call get area here, it's going to be get area of circle. It's going to be called. Here, the third one is triangle. So same thing, get area of triangle is going to be called. If you would call on these objects of type shape a method that is not virtual, then that would be the base type behavior that is called. Okay, it's not always the subtype behavior. It only applies to methods that have been declared as virtual. Okay, so as we may have seen in the previous slide here, the C-shaped class here declares get area and print as virtual. So it's only those two methods that will have the dynamic binding or polymorphism enabled on. For example, there's get name method or any other method that's not declared as virtual. If they're not declared as virtual, they're not subject to dynamic binding. So it's going to be the super type behavior that's going to be called in this case. Only the subtype specific behavior call is going to happen only on those that have been declared as virtual. So you see here that I have the implementation of circle and rectangle, which are a subclass of shape. As we may have seen, get area and print have been declared as virtual in the superclass. Note that here, I'm not redeclaring them as virtual. I could, but I don't have to. That doesn't mean that they're not virtual. I mean, the virtual characteristic, if you want, is inherited characteristic. So if one of the base classes somewhere is declaring a method as virtual, then if any of the other children in the hierarchy or graph are redefining it, then it's subject to being virtual, even though the children classes don't declare it as virtual. So you don't have to have virtual here. You could, but you don't have to. So yes, so the circle defines their own get area, and rectangle defines their own get area, as well as their own print. Okay. Note that how I organize print here. So when you call print of a circle, so because print is a virtual method, if you call print of a circle that is a pointer, an object that is pointed to by a pointer of type shape, then if you call print on this object, it's going to call the subtype specific behavior of print. But because also I organized the code so that print is actually implemented also in the base class. So what it does is to print the values that are the values that are held by the data members that are local to the shape object, that are common to all kinds of shapes. So if you call print on a shape, it's going to print the name and the area. Okay. So that's why when I call print of a circle, first thing I do is call print of the superclass. So you see here that I specifically say call print of the superclass. So it's, here I'm kind of bypassing the polymorphism here and calling print in this manner by specifically say call print of the superclass. And then after the superclass method has been called to print the values that are common for the data members that are common to all the subclasses, then I print my own class specific values. Okay. And of course, I do the same for my rectangle. Okay, another thing that is kind of tricky, seems that everybody should know that, but not necessarily, is that if you declare at least one virtual method in your class or class hierarchy in one of your base classes, if there's at least one virtual method inside of your class hierarchy or graph, then your destructors should be declared as virtual. Okay. So any class that you declare that is a base class that you will use to enable polymorphism must have virtual functions and must declare their destructor as virtual. Okay. So why is it so? So if you look at this code here, so when you execute this code, you declare a pointer to the base class, okay? And then you instantiate it with an object of the subclass. So that's basically saying that because I have this that is declared as virtual, this is essentially going to be executed using dynamic binding, because I have a pointer to the base class, which is then instantiated with an object of a subclass, and there is virtual member functions inside of this class graph. So essentially when I call delete B here, so what is the type of B? B is the type base. So eventually here I would call, I would actually call the destructor of the base class, okay? If I actually don't do that here, then it's going to eventually be, oh, sorry, if I have virtual here, yeah, that's confusing because I enabled virtual here, which is contrary to what I say here. The point here is that the type of this is base. So if you call the destructor on this, then it's going to call the polymorphic destructor, okay? So it's going to eventually call because the object that is inside here is of type derived. So it would eventually call the destructor of derived, which would then not call the destructor of the type base. Okay. So that's why anytime that you have a virtual member function inside of a class that you're going to use polymorphically, you should also declare your destructor as virtual. If not, then you might have a resource leak or memory leak. Okay, so let's go to pure virtual functions and abstract classes. So in Java, you have this notion of an abstract class. It's basically a class for which you cannot declare instances of that class, okay? Which is somehow related to the notion of the interfaces in Java, which you don't have in C++. So there's a relationship between abstract classes and interfaces. Essentially in C++, interfaces, there's no such thing as something you declare as an interface. Essentially in C++, if you want to use or define an interface, then you declare an abstract class. So in C++, abstract class and interface is the same thing. Now the question is, how do you declare an abstract class? There's no such thing, in Java. In Java, you would use the abstract keyword in front of the class keyword in order to declare an abstract class. There's no such thing as the abstract keyword in C++. So how do you define an abstract class in C++? We will see later on that if you want to declare an abstract class, then you need to use this notation here, the equals 0. So you declare a virtual method, and then you have equals 0 here. So we'll come back to that later. So these equals 0 methods are called pure virtual methods. Okay. Essentially, the notion of a pure virtual method means is, as we saw earlier, the name virtual refers to something that exists in essence but does not exist in reality. That for a pure virtual function, that's exactly what that means. You declare a method, and by putting equals 0, you declare that this method does not have any implementation. So a class in C++, a class that has at least one pure virtual method is an abstract class. Okay, so you don't declare an abstract class by putting the abstract keyword. You just put inside of this class a method that is a pure virtual method that has the equal 0 in the class declaration for at least one of its methods. So as in Java and as for any other languages that use language that uses abstract classes, the idea or one of the consequences of having an abstract class is that you cannot create instances of that type of that class. You cannot create objects. You cannot call new on an abstract class to create an object of this kind. So that's why if you have an abstract class, C++ abstract class, you're not allowed to do something like this, which is essentially calling the default constructor of the class shape in order to create an object of type shape. You cannot create an object of type shape. You can create a subclass, an object of a subclass of shape that would have a part which is of the object of the subclass would have a part of the base class shape, but you cannot create an object which is of the class shape for C shape. So that's not allowed because here you're calling a constructor to create an object of this kind, which is abstract. So yes, you were able to create an object of this subkind. You might say, okay, I'm going to create an object of the subkind and I'm going to pass it to my copy constructor. No, you cannot directly call any constructor of the class C shape. In fact, only the subclasses of C shape are allowed to call the constructors of C shape. You're not allowed yourself to call these constructors explicitly in the program. You can't either create an array of shapes. So you might recall in the previous example, I had an array of C shape, but it was an array of pointers to C shape. So I'm allowed to create a pointer to an object of type C shape, but not an object of type C shape itself. For the same reason here, I'm declaring a function that receives a parameter of type C shape as a pass by value. If you remember, when you pass by value, what it would actually do is to make a copy of the object of type C shape, which would result in the constructor being called and then a new object of type C shape being created, which is not allowed. So you're not even allowed to have a parameter of type C shape. You would be allowed to have a parameter which is a pointer or reference to C shape, but not C shape itself. So in order to use an object, so it may seem that abstract classes are extremely limited. The point is that if the real use of abstract classes is that it assumes that it will have subclasses, and that each of the subclasses that inherit from these pure virtual methods would themselves provide a definition for all of the pure virtual methods that are inherited from the abstract class, or inherited from any of their parents in the hierarchy or graph. If you create a subclass and then you implement only some of the, provide an implementation for only some of the pure virtual methods, and you leave some of them undefined, then the subclass you just created would also be an abstract class. So a class that is usable, for which you can create objects in a hierarchy that contains abstract classes. These classes essentially at the bottom of your hierarchy or graph would need to provide an implementation eventually to every of the pure virtual methods that they inherit. Okay. If not, that they would still themselves be an abstract class. So here I said basically that you're not allowed to create objects of type C shape, okay, in any way. But you're actually allowed to declare pointers or references to type C shape. So for example, here I'm creating a reference, a variable S, which is a reference to a C shape, and then I'm actually making it a reference to my shape rect object that I had declared here. Okay. Here I'm declaring a pointer to an object of type C rectangle. Okay. This is allowed. Eventually also I can create a function that receives either a reference or a pointer to an object of type C shape. So that's still also allowed. That's eventually how you're going to enable the polymorphic behavior of these upon these the execution of these functions. So typically, a pointer variable to an abstract class type is declared, then it is instantiated with an object of one of its subtypes, as we saw earlier. So here I'm declaring a pointer to a variable named shape, which is a pointer to a C shape. Then I'm calling new here to create a rectangle, which returns a pointer, which I then assign to this pointer here. Okay. So here, never did I create an object of type C shape. I just created a pointer to an object of type C shape. It just happens that C rectangle, the C rectangle object is also a C-shaped object because it inherited from it. That's how you typically will see polymorphism being created or enacted in a C++ program. So eventually, as I'm calling getArea on this shape, then as getArea is a virtual function, then this is going to be a polymorphic call. Again, if I call print, which also was declared as virtual, then the polymorphism, the late binding is going to be executed to figure out which print function I'm executing here, because print was declared as virtual. If I would be calling a function that is available in the shape class that is not virtual, then the polymorphism would not be enabled here. And then also, when I have any of these two definitions here or declarations for this function, if I pass my object of type C shape here to this function here, it's going to be, yes, received as a C shape, but the pointer is actually pointing to an object of type C rectangle. So inside of this function, if I'm referring to the parameter, then it would lead to polymorphic calls. So there are two main uses of declaring abstract classes. So as I hinted at before, in Java, you can declare an abstract class or you can declare an interface. Okay, these are two very similar concepts. In fact, in C++, they are the same concept. Okay. The fact of the matter is that in Java, you cannot have multiple inheritance. So if you would say a class inherits from another class, if you wanted to also implement a certain interface, then this interface cannot be a class. Okay, so in Java, interfaces are some kind of abstract concept that are not classes, that basically don't have a state. Okay. It gets complicated with multiple inheritance when you inherit from different things that each have their state. Okay, so that's one of the reasons why in Java you can inherit from only one class. You can implement an interface, but interface does not have state in itself. It can have static variables or constant variables, but it cannot have its own state. If it has some values associated with an interface in Java, then these values are common to all the objects and you cannot change their state. In C++, because you have multiple inheritance possible, then you don't have to make this restriction. That's why when you want to define an interface in C++, you basically declare an abstract class. So you can use abstract classes as we saw before. So you can declare your C-shaped class and then declare your getArea member function as virtual, yes, but as also a pure virtual function. The idea here is that there's no such concept of the globally defined concept that applies to all kinds of shapes, such as getArea. Okay, getArea, the way you compute area depends on the specific kind of shape you're talking about. There's no generic formula that you use to compute the value of the area of a abstract definition of a shape. So that's why you say here, yes, there is an area. Every shape has an area, but there's no way you can define it for all of them. So I'm going to be basically saying this is an abstract concept. Okay, that's why I'm declaring as pure virtual. And you let every of the subclasses to implement their own version of this concept. So that's what we saw before here. That's one use of an abstract class. If you want to declare an interface in C++, then you would define a class that has somehow only virtual members. Okay, so that would be exactly the same as a Java interface. Okay, except that in C++, you would be allowed to have some data members for these for this abstract class. Okay. Okay. So that's it for that. So next thing we will see is value semantics and reference semantics, which relates to either or not you're actually turning on the polymorphism in your program or not. So see you later.